Exercise 18 corresponds to exercise 8.1.2. So in the category of groups, show that monics are just the injective set maps. So actually, it is claimed in Weber's book in the context that for any concrete category, monomorphisms are equivalent to injective maps in the theoretical sense. But actually, if you look at other conferences, usually it is said more carefully. It is said that in most categories, concrete categories, more precisely those categories where there is the concept of a free object, like in the category of groups, if there are free groups, then injective will be equivalent to monomorphism. We will say this precisely in this category of groups. Second thing to prove is that kernels are equivalent to monomorphisms whose image is normal subgroup. Let's say firstly the monomorphism are exactly the injective maps. So firstly, recall the definition of monomorphism. F is monomorphism if you could cancel it from left hand side, which means F compose J equals F compose H implies J equals H. This could be deduced from the fact F is injective, which means injective implies this easily. The other direction is what I said. Basically, you need a free object. So let's first say if F is injective, then it implies this is monomorphism. This is very quickly because your question is G equals H, which is the same as is Ji equals Hi for whatever I in big I, because as maps they're the same. If for any elements in their domain they're the same. But the answer is yes, because F is injective, and so F compose G implies I equals F compose H evaluate on I are the same. This is the assumption. Implies that this is just F of Ji, this is just F of Hi. So F of Gi equals F of Hi. This implies Gi equals Hi. The other direction is, suppose it is monomorphism. How do you show that it is injective and map of sets? So suppose it is not injective, which means there exists X and Y different in G such that Fx equals Fy, and then we induce some contradiction. The contradiction is, as you could imagine, we are going to construct some group I such that through some group homomorphism, different homomorphism, so the same element Y is mapped to X, Y is mapped to Y. So G and H are therefore by definition of a map different maps, but because F cannot distinguish X and Y when you do the composition, this is still true. But then this will not imply G equals H, or say being monomorphism would be impossible. So more precisely, suppose F is monomorphism and not injective, we have this. There exists some element x and y such that their image are the same but differently. How do we construct such map, such a group I and different maps G and H? So imagine if just in the category set you could simply just put a set of 1 point, and then 1 is mapped to x, 1 is mapped to y in the category sets, and then both are maps, and then this f, it will map both x and y to the same point because fx equals fy. In this case, although f and j and h are different maps, but f composed with j and f composed with h are the same. They are both the map which map the unique point to fx. And so this tells you that in the category of set, monomorphism implies injective, or in other words, if not injective, then not monomorphism. Because we construct counterexample, f compose g equals f compose h for a particular set, but this does not imply g equals h. So we have to do the similar things in the category group. So what do you have to do? You have to construct a group. It's more difficult because you cannot define whatever you want. You have to make sure G and H are both group homomorphisms. So how we do is we choose construct a free group, and for example we look at this group. Basically this is a free group generated by the set with element 1, and then just use this free group. You could define group homomorphism whatever you want, which means you could map this one to whichever element in another group. So you map one to y in J, and another group homomorphism you map element 1 to x, and then f composed with J, which still equals f composed with H because it basically maps n to if we use additive structure for J, then this would be both be mapped to y to the power n, and this equals y to the power n, but this is also fx to the power n, which means their composition is the same but G and H are different. Secondly, to show that all monic or monomorphisms are all monomorphisms whose image and normal subgroups exactly the kernels, which means kernel is equivalent to kernel as a map, as a morphism is equivalent to monic morphisms plus image being normal subgroup. This is what we have to show. So firstly, one direction is easy, which is kernel is monic and image being normal subgroup. So kernel, firstly, obviously the image is normal subgroup. Just check by definition, because normal means more precisely to call this I. So this is normal because for any element J in J multiplied by the image of kernel F multiplied by J inverse is still in the image of kernel F. This just comes from the computation that F acting on this is still 0. And this is a monomorphism because, as we just proved, any injective map is monomorphism. So the kernel is, by definition, those killed by this group homomorphism map. So it is a subgroup of G. Decoded this is injective map into G. Just the inclusion, if you want. And so in particular it's monomorphism. So conversely, suppose you have a monomorphism whose image In is a normal subgroup of G, then we show that it's actually a kernel of some map. So we construct this map quotient by the image of N, which means you map J to this coset this quotient group, or simply just map J to G bar. And then obviously, firstly, we want to show that this is a kernel, which means I is the kernel of this group homomorphism pi. So check by the universal property. Suppose there is another group H with group homomorphism J, small j to J, such that the composition with pi is 0. We want to show that there exists a unique map H to N, make this diagram commutes. So H composed with H maps to G, and under the action pi becomes 0, means the image of small g is in the I of N. And so notice that N is actually isomorphism to I of N as a subgroup of G, or more precisely normal subgroup of G. And so by group there is group homomorphism I inverse from In to N. So let's say, to make the diagram commutes, the only choice is the composition of this I inverse with G. And one checks this mixed diagram commutes, so it satisfies the universal property.